Hi everyone, I hope that you're all doing well. In this video, I'm going to show you how to conduct a data analysis project where you've got a categorical outcome and a quantitative predictor. This is the final of the four logically possible types when you've got two variables. So you could have a quantitative and a quantitative variable, categorical and categorical variable. Then you've got the somewhat surprisingly actually easier case of a quantitative outcome and a categorical predictor, but now we finally come to the most difficult case, although possibly the most interesting, when you have a categorical outcome and a quantitative predictor. So let's go ahead and run our standard header here to get started. And I'm going to assume if you're watching this video that you have a basic mastery of those other three techniques I've mentioned. And I'm not going to dally too much with the details here. In particular, I'm also going to skip over some of these Stata details. An earlier video in this series explains in some detail, possibly excessive detail, why we do all of this stuff here. So go watch that if you are forgetting, but you don't really need to understand it, except for two parts. The first is this: you need to make sure that you've changed this to a folder on your computer. So you need to set your working directory. And then you need to make sure that you've got data in that directory, or in my case, in a subfolder of that directory. And then you'll want to just go ahead and run this so you can load in the data, and we can double check that we've loaded in the data. Okay, so let's try to motivate this a little bit. So why would we bother with this approach? Well, in a lot of social scientific applications and many commercial applications as well, you might be interested in an outcome that is qualitative. And that is, in general, a tricky bit of business. But there are many situations where you might be interested in simply a binary outcome. So, did someone develop heart disease or not? Did someone choose to join a particular union or not? Did a customer buy a car or not? And if you're interested in that kind of outcome, as I've kind of developed as a theme throughout this series, if you can compress the data into a simple binary outcome, a lot of times that's useful both as a predictor, already covered in this series, but it turns out that actually makes regression of a dummy variable, is what we would call it. That regression of a dummy variable on a quantitative predictor is also actually significantly easier than if you have an outcome where you've got many possible qualitative values. So what we're going to do in this video is talk about a couple of approaches. The first is appropriate for students in 360 and people that are just learning statistics. The second is a little more complex, but I want to show it because it's kind of fun and the results are cool looking, even if you don't fully understand the math. So we're going to primarily stick, however, to this simpler model called the linear probability model, which has some known flaws, but is fine at this level. So let's actually return to the example from the first part of this project. And the first part of this project went over the example, a very simple example of just predicting someone's level of education from their father's level of education. But now let's say we're interested in type of outcome that might be of interest to policymakers or to parents in a particular community. We just want the binary outcome of whether or not someone graduated high school. And we might want to see whether the transmission of class through generation plays some role in that. Now, education is not a direct determinant of your class status, but it's oftentimes bound up with someone's class status. So let's again use the predictor of father's education, but let's just use now as a binary outcome whether someone actually graduated high school or not. Simple. So I'm going to pass really quickly over the analysis of father's education, both because I quite literally use this variable before in this series, and also just in general, you should feel comfortable with these pieces of information, such as the basic summary statistics, if you're doing this video. Now, brief data reminder: don't tabulate quantitative variables because the computer will sometimes just show results that look terrible, and other times will actually, slow down significantly, unless it's very discrete. Here it's very discrete because we've only got 21 possible values of education, 0 to 20, so we can go ahead and print these out. And we see our basic summary statistics. The median, the mean, we can see that this has got, actually in this case, a bit of a left skew because the mean is lower, unlike many other sociological variables. We've also got the third quartile here, first quartile here, denoted by Stata as the 25th and 75th percentiles. Those are the same thing. We see the number of observations, so there were many more missing values of father's education, and that would be an interesting topic to discuss if we had more time. The fact that these are very likely not missing purely at random. But that's more or less all we need to say about this. You can see the standard deviation, which is actually fairly large. The variance, which is a very useful property in proofs because it's computationally simpler, but the standard deviation is more easily interpretable. So those are the basics. Now let's make our outcome variable. I'm going to show this even though if you're watching this, you're probably feeling pretty confident because this does take a little bit of practice. So first, we're actually going to describe education. I forgot to include that here. And the reason we're going to do that, this doesn't print very much information, but the helpful thing that it prints is the value label. And what that does is basically tell us whether or not the, what the mapping from numeric values to actual printed strings associated with those things is. And actually, I'm just remembering that I obtained this not from edu, but from degree. So we actually wanted to describe degree. So we get the value label for degree, and we can go ahead and print that value label now. And what that does is just show us, again, in many other languages, it's called a dict or a dictionary. It shows us a mapping or a key from the values to what you'll see if you simply tabulate degree, for instance. So this is what Stata prints, but this is what's going on under the hood. And we can actually see that by writing tab degree, no lof or no label, and it prints with no label. So this really is being considered by Stata to be a numeric variable. If we come back up here, we can see the storage type, it's a byte, which is a type of a numeric variable. So a lot of times surveys will assign numbers to qualitative outcomes, even though the outcomes really aren't numeric. And we have to be careful when we analyze those outcomes. So it doesn't really mean that this is a truly quantitative variable. That's just a convention in survey research. It started before people were, using a whole lot of computers in their analyses of survey outcomes, but it turns out that it's actually really useful for computers anyways, because computers very often won't work very well if you just have string variables as they're known. And that's a string variable is a case where you literally are saying something like, here, I'll actually show it briefly because this is a video for advanced students. So we'll pull up the auto data set and we'll actually see that make is a pure string variable. So the type of car we have, tabulate make here, we can see this is the type of the car. If we describe make, it's a string, actually. This 18 means that the longest string is 18 characters. But if we try summary statistics here, we'll see that we actually get 0 observations. So we would see that we have 0 observations here, which is obviously not true. So strings are kind of problematic. So coming back to the main point here, we want to go ahead and make this dummy variable, and we'll want to use that set of numeric information that we got. So we'll come back and we'll rerun all of this just to get this back up. Remember that we cleared our data, but the point of writing these do files is that you could see immediately I'm able to get right back to where we were, even though I had previously cleared the GSS and started using the auto data set. So in this case, what we want to do is basically make a dummy variable that just says this person has at least a high school education or higher. And remember that we don't want to include these people, and they're going to be perceived by Stata to be infinitely large values. And that's weird, but that is the missing value convention in Stata. And so we need to be careful about that. So let's write our code very carefully here. We're going to say generate high school grad equals degree greater than 0. So Stata will evaluate this Boolean expression. It'll mark down 1 if true and 0 if false. That's the basis of Boolean algebra. And we want to exclude the condition that people are missing on degree. So let's go ahead and make that and then check our work in the conventional way. And we can see here that it looks like there might not have been anyone actually missing on degree. Let's verify that really quickly, which is kind of interesting. And we actually see that there were no missings, which is good news. So we didn't even have to worry about that. It's just that Stata has, or the GSS rather, has these codes. Maybe some years people were missing, but turns out no one was missing this time. And we can look at the more kind of basic thing here. We see that people were 1s on HS grad is what I called it, if they had a high school, junior college, bachelor's, or graduate degree, and only if they had a less than high school education were they marked as 0. So now let's make our value label. We're going to say label define HS and call it whatever you want. Really, we're not going to use it much after this. 0, no, 1, yes. Make it pretty simple. And here I'm going to label the variable. And so a lot of times you can get the value labels to be pretty concise as long as the variable label is pretty informative. And then in many contexts, Stata will print the variable label. And so then the value label doesn't need to be very long, basically. So it's worth your while to label your variables, which is something that took me forever to learn. And then I would write these long strings in the value label, but this is a better approach. So we can check out our work here. Let's try this now. And we can see respondent graduated high school. I just used R as the GSS does. And we see that we get the same information as if we tabulate degree just really quickly. So this checks out here. So now what we want to do is print those summary statistics. And I've mentioned this before, but dummy variables have really nice intuitive meaning. So the mean is going to be the proportion of people who had a 1 on that variable. And so that kind of checks out. We saw above that only about 11% of people had less than a high school education. So about 89% of people did have a high school education or more, that is. And that's also the same thing as the mean of this dummy here. And then the variance is effectively p times 1 minus p. We'll come back to that. Actually, not too much in this video. I won't go into a detailed proof, but that becomes a useful property to know later on. So I'm going to pass over sort of the material for father's education. I went over this at some length in the other video. We don't really need to go too much into the graphical analysis. If you're doing this type of a project, you should feel comfortable with that stuff. Put up a histogram and a box plot for father's education. For the dummy variable, put up a bar graph. That's basically all you need to do. So let's get to the interesting stuff. So here's the interesting thing. You can actually take a correlation between this dummy and the quantitative predictor. And we're actually going to see a high correlation here. And you should feel intuitively like this is okay, in part because if you looked at the previous video where we had a dummy predictor and a quantitative outcome, notice that that also, although the regression is going to be different from regressing a dummy on a quantitative predictor, the correlation coefficient has no sense in which there is an order. There is no order in correlation. So what that means is that if we could take a correlation coefficient then and then turn it into a regression slope, we should be able to do the same thing going in the opposite direction, and we can. But let's look first at this correlation coefficient. So we can see that there's actually a relatively high degree of correlation. So even though we've in some ways kind of flattened the data, you can see, for instance, if we try to correlate, let's say, education and father's education, we're going to see a higher value here. So we've flattened some of the variation, and as a result, we kind of have a coarser measure. But at the same time, there's also still a pretty strong relationship. So that's the first thing. Now, what we want to do now is actually directly predict whether someone graduated high school. And we're going to run a regression here. It might seem kind of strange, and you might be a little bit skeptical about what this actually means, but I want to explain it. So let's pull up the material first. So we'll get the regression output here. And how are we going to interpret this? Well, what we're going to say is that for a unit increase in father's education, that's going to be interpreted as the change in probability of someone graduating high school. So the reason we can say that, I go over this in a little bit more length in basically a simulation that I show in lecture 10. So see the attached lectures if you're interested. But the idea is that we are basically modeling the underlying probability of the binary outcome as something that is a linear function of x. So we're assuming here that the probability of graduating high school has a linear relationship to father's education. We only see this censored outcome, as it's known technically. So we only see this basically outcome that is like a very rough indicator of that underlying probability. The idea is that there is this underlying probability that we can model as a linear function of x, in this case, father's education. And so we can get a sense of what that looks like if we pull up a scatter plot. We're going to see that this is maybe not the most informative thing in certain respects, or that there might even be problems. So if we take a look at this here, we see, okay, we've got this regression line, but notice that some of the predicted values are greater than 1, which is nonsensical. And we also don't have very many predicted values that are below even 0.5. That's actually fine, but you can see that if you had a different type of set of variables, basically, you could also get predictions logically that are less than 0. So there's a couple of problems here. Additionally, it's really not clear that we should have this linear model. So it's not necessarily the case that we think of probability as being a linear function of some quantitative predictor. In this case, maybe it's a little bit more plausible because the possible values for father's education are pretty limited in the first place, right? It's a pretty discrete variable. But we might think in general that if you're, say, thinking about the relationship between BMI and the probability of having high blood pressure, an example I showed in class, it's probably the case
that you, at a certain point, the effect that your BMI has on your probability of having high blood pressure is more or less exhausted. In other words, you have what are called declining marginal returns. So a unit increase at a particular point on the x-axis is not going to have the same effect as it does in another place. And that's pretty intuitive, I think, to most people. So it might not make sense to say that, for instance, using this model, that you had the same increase in the probability of graduating high school if your father went from 19 to 20 years of education as it did when he went from 11 to 12 years of education. Just sociologically, someone being able to actually get that high school degree has fairly large implications for the sorting process into class when someone enters the job market. In other words, if in your mental schema, you think class is sort of the central sociological variable, and I'll kind of confess my Marxist orthodoxy there. In many respects, I would call myself a purely orthodox Marxist. I would say that that is really central, right? Because you do have these other determinants of class, and one of them is whether you obtain a high school education. That has a really pronounced influence on whether you become a member of the working class or not. So we would say probably that going from 11 to 12 years of education shouldn't have the same effect on the probability of your child graduating high school as if you go from 19 to 20. So we may want to somehow model that. And that's what I'll talk about in the rest of the video. But I wanted to just stress at the level of this class, 360, you can still have this linear probability model, and that's how you interpret that output. So a unit increase in the predictor leads to a beta 1 increase in the probability of the outcome. Again, we don't actually observe that underlying probability. We can't see it here. If you are interested, I thought it would take us too far afield to show the simulation in this video, but I show a simulation of what that would look like. Like if we could actually observe that underlying probability, what would this model look like? It's attached in that lecture 10. Go see it. I spent a little while putting that demonstration together. I think it's probably better than I can do in a short video that's mostly not about simulations, it's about actual practice. But I did want to say a few words about what you could do if you were convinced that this model, this linear probability model, was not actually a good one. Now, this is a kind of advanced technique, so I don't want you to try this necessarily for your data analysis project if you're in my class, but you might want to think about it if you are considering going further in statistics. When you take SOS 62, if you're a graduate student or an undergrad who's doing the concentration in analysis and research or CAR program, you'll spend quite a while on this. So here's the basic idea. What if instead of the underlying probability, which is of course bounded between 0 and 1 being linearly related to x, what if it has a sort of sigmoid shape? In other words, the kind of S shape. And there's actually a function that generically produces these sigmoids that we'll talk about in just a moment. So if x does have that sigmoid relationship to p, in other words, we think that as x increases, the response of p is something like that S shape, quite literally. What does that mean that x actually has a linear relationship to? It turns out that one way you can model that is that x has a linear relationship to the log odds of probability. And odds are not a commonly used concept in basic statistics, but they're really simple to understand and they're common in the real world. So I'm not a big gambler, but if you play a lot of poker or something like that, or you just are betting in general, you probably talk about odds quite a bit. And odds simply are the relationship of p to 1 minus p, or in other words, the probability of the thing happening to it not happening. 1 minus p is often denoted q, by the way, but it doesn't really matter how you write it. It's just a matter of convenience. Here, I think it's pretty convenient to just write it as 1 minus p to remind us what it is. And the nice thing about odds is that they are not bounded between 0 and 1. So consider something simple like randomly selecting a number between 1 and 10. So what's the probability that you're going to select a 5? Well, it's just going to be 1 out of 10, right? And then let's say that you're maybe interested in the probability that you don't select a 5. So that's going to be 9 out of 10. And then if you think, what are the odds of not selecting a 5? We're going to have 0.9 over 0.1. And of course, you can immediately see that that's just going to evaluate to 9. So you have 9 to 1 odds. And what that means is that you have a number from this, you've kind of taken probability, but you've entered it into a function that no longer is bounded between 0 and 1. And that's really good news. But the other problem is that suppose, although you don't have it in this case, that your predictor could take on negative values. And the odds cannot take on negative values because there's no way that p or 1 minus p can yield the negative number. So then the next step is to take the logarithm. And the logarithm basically means for some base, so let's take the simplest case, log base 10, which is maybe the one you learned in high school. The logarithm base 10 of some number a says, what do I take 10 to get a? So log base 10 of 100 would be 2, for example, because we take 10 to 2 to get 100. So you might be wondering how a log can produce a negative number. So let's look at a simpler case because Euler's number, it's very nice. It's got super nice properties that, like, for instance, the derivative of e to the x is a really nice feature. I'll let you kind of do a little bit of refresher on calculus if you want to know more about that. But the nice thing about a logarithm is that you can spit out negative numbers. So for instance, what if you have, say, log base 10 of, I don't know, 0.01? So in other words, what that's asking is what number do we take 10 to get 0.01? And you would think about it and you would say, okay, well, 10 to the 1 is just 10. 10 to the 0 is defined to be 1. And so if I want to get something smaller than 1, I'm going to need to take 10 to a negative, which if you take, say, 10 to the negative 2, you would get 1 over 100, right? That's just how we think about negative exponents. I don't have time to kind of go into a proof of that, but I would recommend if you're interested, you want to think about having, like, powers over other powers, do some cancellations, and you'll kind of get the sense for why we subtract exponents when we divide. And then you can just think about it like 1 over 10 to the 2 is the same thing as 10 to the 0 over 10 to the 2, and you subtract the exponents and get 10 to the negative 2. Anyways, so that's a way that we can basically plug in values that are between 0 and 1 only. Then we can get the entire range of positive numbers from taking the odds. And then because of the logarithm, for some base, we'll spit out negative numbers, even with only a positive input. If that number that we plug in ends up being small enough, we can get the entire range of real numbers. So to come back to our example that I meant to finish talking about, if we're thinking about how do I get 0.1 out of 10, right? So that's just 10 to the negative 1, right? So 1 over 10. And that would be a way that I can plug in a positive number, 0.1, and get out from that function a negative number, negative 1. So coming back to the kind of idea here of logit, which is what this is called, logistic regression, we are saying that the log odds of this basically probability is actually a linear function of x. And there's a reason for that, which is that basically the log odds kind of have this sigmoidal shape. And so when we take x in relation to that, that's actually a linear relationship. So finally, we can estimate the model. So we can say, let's estimate the log odds of this outcome using x as a linear predictor. Then what we do is exponentiate both sides, do a little bit of algebraic rearrangement. And when we do all that, our basic linear model actually ends up in the exponent of e. So it's exponentiated. And that means that our set of predictions is nicely nonlinear for something that we think is probably nonlinear. And I show again in lecture 10 a bit of a simulation of that. Let's see what that would look like in our case here. So we're going to first write logit to tell Stata to run a logistic regression. You'll see that it uses kind of a different method of estimation that I'll talk about in just a moment. But we get these coefficients here and a constant as well. But these aren't really intrinsically meaningful on their own. So what we want to do is predict the y-hats, or you can just call this whatever you want actually. But when I say predict y-hats, basically I'm telling Stata, write down the predictions and go ahead and exponentiate them for me. And then finally, we can go ahead and plot these. So we're going to put up a scatter plot with the dummy outcome and the quantitative predictor and the linear prediction. But then we're also going to put up a scatter plot. There's not going to be a line of best fit because we are more interested in these predictions. But we're going to put the predicted probabilities from the logistic regression up against the others education as well. And let's see what that looks like. And you can see that there's kind of a couple of different ways of looking at this relationship now. So we've got this linear way, but it's got some things we don't like. It extends above one, for instance, and it seems to suggest that pretty much the marginal effect of your father increasing his education by a year is the same everywhere. But I'm a little more drawn to this logistic prediction because you can see that it implies a couple of things. One, it implies that maybe like the key zone for you ending up with a high school graduation or high school degree, that a lot of that impact of your father's education comes when your father goes from having no education at all to something close to a high school degree. It looks like the kind of peak rate of increase here is somewhere around this spot. So basically, as long as your father is obtaining a, kind of like a eighth grade education, it seems like that's kind of the biggest impact. And you might think that's a little weird, but that makes a lot of sense actually, because there are other influences on your high school degree status besides your father's education. And you might think about it like, well, there's so many social influences, like, for instance, the increasing criminalization of truancy, the fact that it's really hard legally to not get a high school education. Like in a lot of states, there are policies that almost force people to get one. Um, that basically what that means is that your father's education no longer has such a strong influence. And the only way it might have an influence is if your father has a truly tiny degree of education. Um, I don't mean to say that pejoratively, but tiny in the sense of like really far below the median. And then maybe it has more of an impact. Like at that point, even net of those other factors, you're thinking, okay, the father's education could still play kind of a key role in this situation. But what this model also suggests is that when we get to, for instance, the point at which your father has even a 10th grade education, those other influences seem to be kind of making it so that it doesn't even really matter that your dad didn't graduate high school himself. At that point, the marginal impact of your father's education is actually relatively small. I think that model actually does a nicer job predicting reality. Now, this is not necessarily a proof that the underlying probability does have this shape by any means, but what it seems to suggest is a story that I think is more plausible, right? So, in other words, we're saying it seems more plausible that probably at a certain point, your father's impact on your own education becomes attenuated. So, definitely here too, if you think about like the case where your father is maybe going from a high school college education to a graduate degree, you might think it's probably at that point not making a giant impact on whether you graduate high school, because at that point you have an extremely high probability of graduating high school. That makes more sense to me than this linear model. So that's kind of a cool way into higher level stats. And notice that here we've also kind of constrained the model so that it can't give predicted probabilities greater than one. That was just a feature of how we estimated it when we said the linear relationship of x is to the log odds, not to the actual outcome. And so that's a nice feature of the model as well. And here in this case, we also, it's not relevant here, but we couldn't possibly get predicted probabilities below zero as well, whereas this linear model would give it to us if we ask that it do. So I did want to give a bit of an intuition for the way that this works mathematically, because it's a little bit complicated, but it's also very interesting and worth knowing. So this is not going to be a rigorous proof, but it's just kind of a heuristic approach. So how is it that we actually come up with these estimates? Well, the first thing we want to do is write down for any fixed sample size and fixed number of successes, the basically binomial distribution, which gives the probability of observing that number of successes out of that number of trials. And so that's n choose k times p of x to the k times 1 minus p of x to the n minus k. Again, we fix the values of k and n, and then we can actually just discard this binomial coefficient, because for a fixed n and k, it's just a scalar multiple. So this is n choose k is not a linear function of k. It's actually kind of got an interesting normal shape. That's a really nice connection, that those values in the rows of Pascal's triangle actually kind of look like a normal distribution. That's not a coincidence. But you don't need to worry about it for a fixed n and k, because then you're just multiplying by whatever that is. So we discard that, and then we basically go ahead and we take the log of the outcome. So we log this left-hand side here, and then we take the log of the right. And then we do a little bit of algebra until we end up with basically the logarithm of p over 1 minus p at a certain point. I'll show you a link in the comments to a derivation of that. Cosma Shalizi's book is a really nice example of that. So we go ahead and do a little bit of algebra there, and we sorry. So we go ahead and do a little bit of algebra until we get that basically logarithm of p over 1 minus p. And we said from the outset that we believed that to be a linear function of x. So then we swap back in our basic linear function. And then finally, we're going to find values of the beta naught and beta 1 that maximize the so-called log likelihood function. This is an interesting approach to estimation. It's different than the so-called method of moments that we have discussed primarily in my class. So what we do is we actually take the sample as fixed. So normally we think about the probability distribution as fixed. So we have a fixed PDF or PMF, and then we plug in possible sample values, calculate their probability. But now what we do is we actually fix the values of the parameters, the sample here, and then we pass through different parameters. So in this case, we're going to write basically the PMF as a function of the beta naught and beta 1, and then put in possible values that maximize basically this log likelihood function for a fixed n and a fixed k. And it's still more complicated than that because the calculus involved isn't exact. You end up with a transcendental equation. And what you need to do then is use an approximate solution. So Newton's method works. And that's why we saw here this business with these iterations. Basically, that's Newton's method. And that's beyond the points of our course. If I taught this, I would need to actually brush up on some of those details myself. But that's the basic idea, is how you do this. Maybe just of interest to people that are watching and have a kind of keen interest in this material. So anyways, that's logit in the linear probability model. I hope you stick with statistics. Thanks for watching.